So, welcome everybody to this session of the joint seminar between the ICMAT and the three universities in Madrid. So it's a pleasure for me to introduce Máté Matolcsi from the Rényi Institute in Budapest. He's also a professor at the Budapest University of Technology and Economics. And he's an expert in Fourier analysis and additive combinatorics and functional analysis, among other things. And his research has been widely recognized. For instance, he has won recently a Frontiers of Research Award. And he's a doctor of the Hungarian Academy of Science. And he will talk us today about the Fuglede conjecture, which is very interesting because he at the same time has proved and disproved this conjecture. So of course he has proved the cases where it holds, and he has disproved the cases where it doesn't hold. So I let Máté start. Thank you.
Thank you very much, and thank you for the invitation and having me here. And indeed, it will be a talk mostly about Fuglede's conjecture and some related issues. And indeed, we will see that some of the cases, some special cases, important special cases of the conjecture turned out to be true, and some turned out to be false. And the most recent one is a joint work with Nir Lev, and this will be the highlight of this talk. And so I start with the introduction of spectral sets, which is maybe not a familiar concept for all of you. It will be a bit obscure at the first sight, but it will probably come to light later in the second slide. So you have a bounded measurable set in a d-dimensional Euclidean space, and you have some discrete point set. You should imagine this as an infinite discrete point set also in the d-dimensional space. And you say that this discrete point set is a spectrum for this omega if the system of these complex exponentials with frequencies from lambda, they form an orthogonal basis for the L2 space of omega. As I say, when you hear it for the first time, it's a bit obscure, but when you think of it, and we say that lambda is a spectrum of omega and omega is spectrum. By the way, the spectrum is not necessarily unique. It may have other different spectra as well. And when you think of classical Fourier analysis, then it really shows you why this concept is natural. Because what is classical Fourier analysis? Well, you have Fourier series on the unit interval or Fourier series on the unit cube. So you take the unit cube in a d-dimensional space, and you take the integer lattice, and we know from Fourier analysis that every function in the L2 space over the unit cube can be expressed as a Fourier series with integer frequencies. So that's exactly, if you go back to the definition, that's exactly says that the integer lattice is a spectrum of the unit cube. So the main problem is what other sets are spectral? Well, the unit cube that's classical Fourier analysis, but are there any other sets that are spectral? And if so, how can we characterize them? And this notion was introduced by Ben Fuglede in 1974, a Danish mathematician mainly working in operator theory. And unfortunately, he passed away last year at the age of 99. He was still in good health, but he passed away in 2023. And he was working on properties of partial differential operators, and he posed the problem. Well, he made the definition of spectral sets, and he posed the problem about them. He was trying to characterize spectral sets. And before we move on, the motivation of Fuglede came from partial differential operators, which is on the Euclidean space, but the whole concept of spectral sets make sense on any locally compact abelian groups. Namely, if you have an LCA group, then you can say that A is spectral. Okay, you have a Haar measure on it, you take a bounded measurable set, and you take the function space L2, and if it admits an orthogonal basis of group characters, so some set S from the dual group such that the elements of S restricted to your set A form an orthogonal basis of the L2 space, then you call your set S as a spectrum of A, and A is spectral. And there are some notable examples of this. Well, the easiest case is finite cyclic groups, finite and possibly non-cyclic abelian groups, or the integer lattice, or the torus to the d-dimensional torus, or the one that we started with, the d-dimensional Euclidean space. And the second concept that I want to connect spectrality to is tiling. Tiling is a concept that is familiar to everyone, even if you are not a mathematician. Tiling will make a lot of sense. Because what is tiling? Well, we say that a set omega, again, a measurable bounded set in the Euclidean space, it ties the space by translations. If you have some translated copies of omega situated at different positions, and they cover the space unilaterally up to measure 0. So there may be overlaps of measure 0 or gaps or measures of measure 0. We don't care about those. That's a usual concept of analysis, that you disregard problems of measure 0. And so this is, for example, one object that can tie the three-dimensional space. And again, the notion of tiling also makes sense in any locally compact abelian group with respect to Haar measure. So again, you can allow measure 0 overlaps or gaps. And I have to make a few side notes about tiling, because there are many interesting problems related to tilings, and some of them have been solved in the last couple of years, and some of them you may have heard in the news. So, for example, this you might not have heard. This is the periodic tiling conjecture. So it says that if you have, so it's true in the two-dimensional integer lattice. So if you have a finite set in Z2 that tiles by translation, then it can also tile fully periodically. So first of all, okay, we have to discuss this a little bit, because you would think, is it not true that every tiling is periodic? Because in the real line, if you make a tiling, it's going to be periodic. But however, when you move to higher dimensions, then all of a sudden, tilings are not necessarily periodic. I didn't include a picture, but I can explain in a second. So even if you take just a unit square, of course you can tile it in a periodic way. That's the trivial way to do it. But what you can also do is to just tile one vertical line with your square, and then the next vertical line you also tile, but you shift a little bit, and the third line you shift also. And if you make these random shifts, then you will have all these vertical strips, all of them a little bit shifted with respect to each other, and then it will not be fully periodic. It will still have one period vector, the vertical one, but not another one. And it's easy to see that if you go higher with the dimension, then you can mess up all the period vectors. So you may have a tiling even with a cube which is not periodic at all. It doesn't have any period vector. But your feeling is that this is a little bit of a cheating, because you can, if you would like to tile periodically, you can. So that's the periodic tiling conjecture, that whenever you have an object that you can tie the space with somehow, then if you are clever enough, then you can do it in a fully periodic way. And this was supposed to be a conjecture, and you are alone, you only allow translation. And this was a reasonable conjecture which stood for a long time, and it's non-trivial even, okay, it's trivial in dimension 1 or almost trivial, but in dimension 2, it was not proven for a long time until 2020 by Bhattacharya. And then, okay, there is a side note here that, wait a minute, just in the news, I saw a Penrose-like aperiodic tiling, right? So how does this, I mean, seemingly what I'm saying is simply not true, because they just had, you must have seen this picture in the news, that you have this object of a hat or a shirt, which whatever you like to call it, and this object ties the two-dimensional space only in a non-periodic way. So how does this compare with the result of Bhattacharya, that everything, every tile can tile fully periodically? Well, there are two things. First of all, this is in the integer lattice, and this is in the Euclidean space. But even more so, the problem here is that rotations are allowed. And here you have only translational tiling, right? So these are two different notions. And indeed, an aperiodic tile exists already in dimension 2, if you allow rotations and reflections. But if you go to the integer lattice, then it doesn't exist if you only allow translations. Yeah, so it uses rotations and reflections. And what came to me as an even bigger surprise is that the periodic tiling conjecture has been disproved last year by Terence Tao and Rachel Greenfeld, maybe 2 years ago. They construct an aperiodic monotile, so something like this, an object which can tile the space. Now the space is only the d-dimensional lattice, but it can only tile in aperiodic manner, which is pretty strange, but the dimension is not 2, it's not 3, it's some billions. So I don't think even the paper actually specifies the dimension. It's high enough dimensions, the constructions work. So somehow it tells you that as you increase the dimension, the complexity of the tilings seems to increase. And things can happen in high dimensions which don't happen in lower dimensions. So aperiodic monotiles can happen in large dimensions. And now we go back to Fuglede, his theorem and his conjecture. So in his paper in 1974, Fuglede proved that whenever you have a lattice tiling, so again, we have to make a distinction, periodic tilings and lattice tiling. Well, a lattice tiling is a periodic tiling in which you only put your object into positions of a discrete lattice. In a periodic tiling, it's not quite so. You tile a fundamental region of your lattice with some copies of your object, and then periodically you extend. So these two things are not exactly the same, and lattice tilings are just one particular case of periodic tilings. And what did Fuglede prove? Well, he said that if omega tiles the space by translations with respect to a lattice, for example, the cube, or you can think of the hexagon in the two-dimensional space. The hexagon also ties the space with the lattice. Then it is also spectral, and actually he says what the spectrum of omega is. Well, you just take the dual lattice L star. The dual lattice is defined as all the points such that the inner product with the points of the lattice is an integer for all lattice points. You take the dual lattice and it will form a spectrum of your set omega. So he established this connection between spectral sets, a seemingly obscure notion, and tiling sets, a very intuitive geometric notion. Oh, and okay, so here are some. So what happens is that, of course, you have these nice pictures. All of them are like this horse, let's say. Of course, it's a it tiles the space in a lattice manner, so it's also spectral. So all of these are spectral sets, even though you wouldn't necessarily imagine so, with all this definition of the L2 functions being able to expand with respect to some exponential system, but they are, because they tile the space with a lattice, so the dual lattice forms a spectrum of them. So all these sets are spectral. And then Fuglede formulated the spectral set conjecture, which is a natural next step. So he said, maybe it's true in more generality. If we don't require lattice tilings, but any tilings, maybe a bounded measurable set is spectral if and only if it can tile the space by translation. It would be a nice characterization of a somewhat obscure notion by another notion which is more intuitive. And again, I make a remark that the conjecture, of course, makes sense in any locally compact abelian group. You have spectrality, you have tiling, both notions make sense. You can conjecture whether the two things are the same. Fuglede made his conjecture in the Euclidean space, but he already, in his paper, he made remarks that all these notions make sense in LCA groups. And for example, he made some observations. First of all, the theorem that we talked about one slide ago, that lattice tilings implies spectrality, but he also said that, okay, let's just consider a few very simple objects like a triangle or a disk in the two-dimensional space. Is it spectral or not? Clearly the triangle and the disk doesn't tile the space. Once again, rotations and reflections are not allowed, so that the triangle cannot tile the space by translation. And he indeed proved that these two objects are not spectral either, so it's kind of a minor result pointing in the direction that maybe his conjecture is true. And then there were a number of results obtained, positive results supporting the conjecture. Let me mention one of them. I don't want to mention all of them. They were very particular results. And like, for example, Josevich, Katz, and Pedersen proved that if you increase the dimension, Fuglede only proved in dimension 2, but if you increase the dimension, the unit ball or any ball is still not going to be spectral for any dimension. Maybe it's not so surprising. Anyhow, we will see a proof of this later in the talk, a different proof than the one given by Josevich, Katz, and Pedersen. So there were a lot of minor results supporting the conjecture, but then Terence Tao, Fields medalist Terence Tao, in 2004, back at the time he was not yet Fields medalist because he received it in 2006. Anyhow, he disproved the conjecture with a very nice idea, constructing a spectral set which does not tie the space in dimension 5 and higher. So how was this example set up? Well, first of all, the example looks like a finite union of unit cubes arranged in a special configuration. This is just a picture of unit cubes. It's not really the configuration that Tao's example corresponds to. But I can explain how his example is built up, because it's very ingenious, but it's also quite simple. Simple in a way. Once you saw it, it's simple. Maybe before that, what happened later was that Mihalis Koluntzakis and myself, a couple of years later, we constructed, also in dimension 5 and higher, sets which tie the space, but they are not spectral. So we are now coming to Jose's introduction that I disproved Fuglede's conjecture in full generality, in this sense that I constructed counterexamples. Tao constructed counterexample to one direction, and we constructed with Mihalis, we constructed to the other direction. And this happened for dimensions 5 and higher, and in the later years, with my work and several co-authors, the dimension of the counterexamples was reduced to 3. So actually, we know that Fuglede was wrong in dimension 3 and higher. And all the counterexamples look like this: a unit cubes arranged in some special manner. And we still don't have counterexamples or proofs for dimensions 1 and 2. So the conjecture is open, and there are many indications that maybe in dimension 1, actually the conjecture is going to be true. Dimension 2, I have no guesses whatsoever. I'd rather say there exists counterexamples, but I'm not sure. And I explained the strategy of the counterexamples because it's easy to understand, and then you will understand why we end up with unit cubes arranged in special manners. The first step is to find a counterexample in a finite abelian group. This is the non-trivial step. As I said, you can take any locally compact abelian group and try to prove or disprove the conjecture. So why don't we take a finite abelian group and prove or disprove the conjecture? And it turns out that it's particularly easy, well, easy if you are Terence Tao, but anyhow, it's particularly easy to find a finite abelian group in which there is a spectral set which does not tile the space. This is related to the existence of certain complex Hadamard matrices. And once you do that, so you have a finite abelian group, you embed it into some dimensional integer grid. So then you have a finite number of points in the integer grid. And then finally you embed it to the d-dimensional space by simply adding the unit cube wherever you had the points in the integer grid. So you end up with a configuration like this. And that's how you end up with the disjoint union of unit cubes. If you do it carefully in a 5-dimensional space, you will get a spectral set which is not a tile. And then we did the same strategy with Mihalis Koluntzakis in the other direction to make a set which is a tile but not spectral. The major difficulty, I mean, these two steps are almost automatic. There has to be a little bit of care and estimation of this and that, but these are automatic. This is the tough part, to find the finite abelian group in which you find a tile which is not spectral, and we managed to do it. And then we reduce the dimensions of the examples to 3. So in fact, now there are counterexamples which you can actually imagine because they are 3-dimensional.
The first embedding, what kind of map is a prime and
yeah, well, the first embedding is it's what you would imagine. So if you have so any finite abelian group is a direct product of groups of prime or prime powers, and then for each factor you increase the dimension by 1, and then you think of it as a big box, your finite, and there are positions in the box, and those are the positions here. But there is a trick which I didn't want to mention here, but there isn't a trick that it's not enough to put one box, but you have to put several boxes one after the other and repeat the pattern again and again. So if you had a counterexample in a finite abelian group consisting of, say, 6 points, then it's not enough to have those 6 points here, but you have to repeat it 1,000,000 times, and then you have 6 million points, and that will be your example, which is going to be a spectral but not non-tile. But as I say, it's fairly automatic what you do. So one natural question is what happens with connected sets, because we always end up with this, we always end up with these unit cubes in space scattered around somewhere. They're not even connected. And the original, if you read the original paper of Fuglede, then he started with connected open sets because he wanted to study partial differential operators. I mean, if your set is not connected, then the partial differential operators act completely independently on one or the other. So he always considered connected open sets. So you might wanna say, well, this is a counterexample, but Fuglede wouldn't be very happy with it because it's not even connected. But what happened? Can we make the counterexamples connected? And it turns out we can. Just a result last year, Mialis Koluntzakis and Rahel Greenfeld again, they made a construction like if you have a, I mean, you're not supposed to understand this picture, but the conclusion is that if you have a disconnected counterexample, which is like the blue dots here, the blue cubes, which are disconnected, you can increase the dimension by 2, and you can make these kind of bridges, and you make a connected counterexample. So the point is that at the end, you can connect the counterexamples and make, so even Fuglede would be probably happy saying that, okay, I can see that there are connected open sets which are spectral but not tile, or which are tile but are not spectral. But of course, there is an increase in the dimension. So the discrete cubes they work in dimension 3, but if you want to make them connected, then it only works in 5 dimensions or higher. Maybe there are examples in 3-dimensional space, but this proof only works if you increase the dimension. And then there was one last, okay. There was one last collection of sets, which was a natural collection of sets where the conjecture was still believed to be true. And that was convex domains. If you have a convex body and it ties the space, or it's spectral, these two things are the same. And that's exactly what we managed to prove with Nirlev a couple of years ago. So one direction is already obvious from what we have seen from the previous slides, namely, if something ties the space, of course, there are many results in geometry for convex bodies that ties the space. They cannot be arbitrary. So what happens is, it's a result from the 50s, rediscovered in the 80s, that if you have a convex body that ties the space by translation, then, first of all, it has to be a polytope. And it has to admit a face-to-face lattice tiling. So again, maybe there are other tilings too, just like I explained with the cube. You can mess up your lattice tiling, but if you like, you can do it in a lattice manner. So this is what it says. Has to be a convex polytope, and it can. If you like to tile it with a lattice tiling, you can. And as a corollary, if you put together the results before, we immediately get that if a convex domain tiles the space, then it's spectral, because we had the result from Fuglede himself that if you have a lattice tiling, then the dual lattice is a spectrum. So that was known already, that one direction is trivial in the sense that you put together results from geometry with results of Fuglede, and you get that anything that ties and convex has to be spectral. And also in low dimensions, like 2 dimensions, it was proved by Josevich, Katz, and Tao, again 20 years ago, that indeed the conjecture is true. But yeah, I mean, this we all know, that if you have a convex body that tiles in 2 dimensions, it has to be a parallelogram or a symmetric hexagon. This is known from geometry. And what Josevich and Katz and Tao proved, that the converse is also true. If something is spectral and in 2 dimensions and convex, then it has to be a parallelogram or symmetric hexagon. So Fuglede's conjecture in 2 dimensions is true for convex body. And what happens in 3 dimensions? Well, the situation gets trickier because there are many more objects that tile. Namely, there is a characterization of translational tilings in 3 dimensions from the 19th century, that there are 5, essentially there are 5 different tilings of the 3-dimensional space, and these are the 5 different tilings: the cube, the hexagonal tiling, and, well, these are not so well known. And what Nirlev and Rahel Greenfeld did a few years ago was that if you assume that you have a convex polytope, and it's spectral, then they proved that indeed they fall into one of these categories, so it ties the space. So in a way, they prove Fuglede's conjecture for dimension 3, but with the extra assumption that they assume not only convexity, but they pre-assume that it's a polytope. So if you just assume it's convex, that the proof doesn't work. So yeah, so the conclusion is that Fuglede's conjecture in R3 is true for convex polytopes. And what we did a couple of years ago, Nirlev and myself, was that we used a completely different methodology of proof, and we proved that the Fuglede's conjecture is true for all convex domains in RD. So if we saw that one direction is true, if it ties, then it's spectral, but we proved the other direction that if it's spectral, then it has to be a polytope, and it ties the space by translation. So we, in this way, I come back to José's remark saying that I proved and disproved Fuglede's conjecture because in full generality, I gave counterexamples, but in the convex settings, Nirlev and myself, we proved it for any convex domain. So in all dimensions. And for this, we needed a new strategy of proof. So before telling you the new strategy of proof, I should say something about the old strategies of proof. And that's pretty simple. The strategy is simple, but the applications get more and more involved, and they always seem to get stuck. So the traditional approach is to analyze the zero set of the Fourier transform. So you start with a set omega, you take its indicator function, and you take its Fourier transform. It has a zero set. And it turns out that the spectrum must have this relation that any two, so remember, spectrum is the frequencies of your exponentials. And the difference of any two frequencies has to fall into the zero set of the Fourier transform. This is very simple. If you write out the definition of spectrality, it just follows from the orthogonality of the exponentials. You want a complete orthogonal system, and if you write up what orthogonality means, it means exactly this, that when you take the difference of two frequencies, then it has to be in the zero set. So then you start with omega, you take the zero set, this is the zero set of your Fourier transform, and what you are trying to do is to take, of course, the picture is finite, but the spectrum at the end has to be infinite. So you want to have infinite number of points arranged in such a way that the difference of any two of them falls on the red lines, which is the zero set. And not only that, but you need a complete orthogonal system. So if the difference is in the zero set, that gives you orthogonality, but doesn't give you completeness. What gives you completeness is basically you have to have the right density of these points. And basically all the proofs before about spectral sets were depending on this strategy of analyzing, because of course you can analyze the zero set at least asymptotically. Even if you don't know the exact zero set, you can analyze it asymptotically, and you can make conclusions about how large a point set can be if its different set is in the zero set. But we found a nice observation. Actually, it's a somewhat interesting story that we started to work on a completely different problem, a side problem of Fuglede's conjecture, which I'm sure it wouldn't have generated much interest. But then, as we were working on it, we came to this new notion of weak tiling. And once we realized that this is a nice observation, where can we make an application of it? Then we realized that convex bodies is exactly the right scenario where weak tiling, you will see in a minute that weak tiling really is suited perfectly for convex bodies. So what is weak tiling and how did we find it? Well, it's something that I call spectral duality. And what is it? Well, if you have a finite group, finite abelian group, then if you have a set A and it has a spectrum S, then again, let's recall, the set lives in the group. S is the set of frequencies. So it's, in this case, it's a set of characters. So it lives in the dual group. And the characters restricted to A make an orthogonal basis of L2A. So your set lives in the group, the spectrum lives in the dual group. But then there is a duality. If you consider S as your set, then A itself acts as a spectrum of S, and A lives in the dual of the dual, which is again which is isomorphic to the original one. So there is this duality relation that if A has spectrum S, then S has spectrum A. Now, this doesn't make any sense if you go to an infinite group like the Euclidean space, because you start with the bounded region A, bounded measurable set. Then the spectrum is a discrete set of frequencies. In what sense can I take that discrete set of sequences and ask what is a spectrum of that? So somehow the relation is not symmetric anymore. But there is a spectral duality has another formulation, a functional formulation, which is the following. Which already makes sense not only in finite groups, but also in the Euclidean space. If you have a set which has a spectrum lambda, then what happens is, this has been known for a long time, then what happens is that you take the Fourier transform of your indicator function of your set, absolute square, and you convolve it with one lambda, which is a Dirac measure situated at lambda, then you get a functional tiling of RD. So what does this mean? Well, this is a non-negative function, right? And you position it to the places of lambda, your spectrum, and you add them up. That's the convolution, you add them up, and then you get a constant function. Well, this constant has to appear depending on the volume of your body that you started with. But basically, while this function is waving, if you put it to the positions of lambda, what you will come up is a constant function. And maybe this formula, I mean, still this doesn't make sense if you want to apply spectral duality. Maybe we can still turn this around. So what would be the dual version of this? I would say, well, if this is true, then let's just switch everything. And instead of one lambda, you take one omega. Instead of 1/2 omega squared, you put 1/2 lambda squared. You switch everything and you hope that it's still constant. It still doesn't really make sense. Okay, this guy has a meaning. It is simply an indicator function. This guy doesn't have a meaning. But nevertheless, so it still doesn't make sense, but it makes a little bit more sense than the previous spectral duality. And indeed, we can make this rigorous with a bit of measure theory and analysis. And how to make this rigorous, I'm not going to say the details, but it's a technique that comes from crystallography. So it turns out that so we want to make sense of this relation, right? And that's the critical point. How do you assess what is this 1/2 of lambda squared? It doesn't make sense. But what happens is it can be replaced by a suitable Borel measure gamma in such a way that the indicator function of omega convolved with this Borel measure gamma is indeed a tiling of the space, such that gamma around the origin is only the Dirac mass at 0. We will understand it in a second with pictures, hopefully. But the way to make this measure is a measure theoretic argument, which comes from crystallography in which it was studied already. So there is a theory of diffractions. When you want to analyze an atomic structure and a molecule structure, what they do is they bombard it with X-ray beams, and then the beams get distracted, and then they make some conclusions about the structure of the crystal. And within that theory, we found something that was an idea that was good enough to produce this measure gamma. So it's as I say, sometimes we say that mathematics is very important in applications, but it's now the other way around. Applications has turned out to be important in mathematics. So it was good that this theory was already available. So let's try to understand what this means, what weak tiling means. So we say that omega can weakly tile if there is a positive measure mu such that the convolution is this. Now is the indicator function of sigma. So what does this mean? Well, this is just the definition of the convolution. It means that you have an object, let's say this octagon, and now you are allowed to use weighted copies of this object and put them to positions wherever you like, and these weighted positions should overlap in such a manner that the overlapping gives you exactly weight 1 over each point. So this is obviously a generalization of tilings, because in a proper tilings, you put disjoint copies so that every point is covered, well, up to measure 0. Every point is covered exactly once. Now, we don't necessarily require disjoint copies. They might overlap, but the overlaps has to compensate each other in a way that at the end, everything gets covered exactly once. And so what we get with this crystallography and measure gamma is that if a measurable set is spectral, then it can weakly tile its complement by translations. And tiling its complement is also easier to understand if you think of in the following way. Let's say you have this octagon as an object, and let's say you put it down here at the origin at weight 1. Now, tiling the complement means that now you are allowed to make shifted copies in such a way that all the surroundings has to be covered exactly once, every point. So in a way, probably it's easier to think that, okay, I want to tile the whole space, but at the beginning, I'm forced to put down my object at weight 1 at the origin. If you don't force yourself to have that weight 1 at the origin, then the notion becomes trivial, because you can just average out. If you put a small weight everywhere and you average out, then whatever object you start with, you're gonna get a weak tiling. But that's not the case if you are forced to put your object there at weight 1, and then you have to build around things in such a way that all other points in the complement are covered with weight 1, with possibly overlapping copies. Again, with the proper tiling, it's obvious. If you have a shape which tiles properly, then you just put everywhere with weight 1 copies which are disjoint and tiled properly. That's easy. But if it's a non-tile, like an octagon doesn't tile, can you put possibly overlapping copies in such a way that everywhere in the complement you cover every point at weight 1? And let's see some applications. Like a fairly trivial application is that if you have a measurable set which has a hole in it, like, okay, this object, this annulus here, and there is this hole inside it. I say that this cannot be spectral. Why not? Because if it was spectral, then it should be able to tile its complement weakly. But how can it? If I put this down at the origin at weight 1, how can I possibly cover the inside with other copies? If I try to build other copies, even overlapping or whatever copies around it, if I want to cover this hole inside, I have to intersect this region, which already had weight 1 to begin with, and then you will have more than weight 1 here. So that's not possible. So whenever, and this kind of theorems were impossible to get with the old strategy of analyzing the zero set of the Fourier transform. Let's see another application about the ball. Ball in any dimension cannot be spectral. Why not? I can convince you very quickly, because it cannot weakly tile its complement. Why? Because you put your object, the ball, at weight 1 here, and then you would have to build around some weighted copies of the ball in such a way that everything gets covered exactly once outside. But then let's look at this point, which is just outside. Let's look at the point which is just outside the original copy. How can you cover that point? Well, basically, you have to put a disk there with basically almost weight 1, right? If you are very close to the boundary, if you put anywhere else, you cannot cover that. You have to put there. But then what happens if I consider another point which is close to the boundary? I have to put this one at almost weight 1, and I have to put this one also at almost weight 1. This one because to cover this point, the other one to cover that point. But then they're gonna overlap, and this overlap is gonna be already covered twice. So that's not gonna work. So it's kind of an obvious argument to say that it cannot weakly tile its complement, so it cannot be spectral. So that's not the original proof of Josevich, Katz, and Petersen, but it's an obvious geometric proof. And you can already feel it here that convex bodies have they come into this argument very nicely, because you already feel it that with a clever generalization of this argument, you can prove that any convex body which ties the complement weakly has to be a polytope. It cannot have curvature, because it's not gonna fit. So yes, you can prove it that it has to. Oh, sorry. What happened? I pushed something wrong. Yeah, so you can prove that if you have a convex body that weakly ties its complement, then it has to be a polytope. It cannot have curvature. And you can also prove that actually it can tile properly, which then settles Fuglede's conjecture, because if something's spectral, then it weakly ties, and then it tiles properly. So I'm not going to go through obviously the proofs, but these are the major steps. First you prove that it has to be a polytope. It cannot have curvature. This is something that I might have convinced you with the previous slide. The second is that it is centrally symmetric, and all the facets are centrally symmetric. Quite conveniently, this was already known if omega is spectral. So if omega is supposed to be spectral, then this result was known from the literature. So we could just refer to it without proving it. But actually, it turns out that if you assume weak tiling, then this also follows. But we could just refer to the literature that all spectral sets have this property. And then there is a third condition. Once again, in geometry, there are conditions which characterize tiling for convex bodies. And one of them is central symmetry, and facets are being central symmetric. And there is a so-called bad condition, which I'm not going to explain, but it's somehow a condition on the structure of the facets. And this can also be proved, and this proves that your spectral set is properly applied. And here I come to a challenge to the audience. So find any group whatsoever, what you like, finite groups or integer grid or Euclidean space, torus, whatever you like. Find any group and any set which ties weakly but does not tie properly. This is a non-trivial task. You can answer me, and there's one more slide, and you can answer me at the end of the talk. But yeah, if you listen carefully, you can put together results and you can answer this question, but it's non-trivial. And so what other research directions are going on right now with weak tiling? Well, weak tiling comes up, for example, maybe the most interesting one is cyclic groups, because any tiling of the integers is periodic, so it's basically a tiling of a cyclic group Zn. And we still don't understand all the tilings of period n. And maybe it is true that all the tilings are the same as weak tilings. And weak tilings can be studied with linear programming. So in a way, tiling questions are integer programming questions. You have to find positions where you put your tile, and weak tiling questions are linear programming questions because you are allowed to have a weighted copies, and then all this convolution comes up as a linear program. So basically, what we are trying to do is to do the linear programming relaxation of tiling, and it may turn out that in cyclic groups, the two things are the same. Weak tilings and tilings are the same. And if they are the same, then maybe linear programming will tell us something about the structure of those tilings, and maybe we will either solve Fuglede's conjecture or Cohen-Meyerowitz conjecture. So there is a Cohen-Meyerowitz conjecture about cyclotomic divisibility, which should characterize tilings of the integers. And if we can understand weak tiling and they coincide with proper tilings, then we might have some bearing on the Cohen-Meyerowitz conjecture. So basically, that's the research direction right now. And so thank you very much for your attention.
Are there questions
or answers?
You were considering spectral sets respect to L2 of A. So you're considering the Lebesgue measure, the Planck Lebesgue measure.
Yes.
What happens if you consider other measures? You can have different spectrum, of course.
Yeah, this is being done, but I haven't done it. So they are so-called spectral measures when you don't consider the Lebesgue measure, but you start with some iterative function system, and then they define you a measure, and you can ask whether that measure, the L2 space corresponding to that measure, admits an exponential basis or not. And there are some, unfortunately, there are some interesting results about it, but there is a big industry now. Lots of Chinese PhD students started to jump on it, and they produce one paper after the other, which is, and usually they don't contain really new ideas. And
but there are some results like Paul Torasti telling you how this spectrum should be. It's also related to the operator theory. It doesn't come from partial differential operators. It comes from compact perturbation of zeta-joint operators, and how this measure, the spectral measure, is coming. Have you?
I haven't considered those, but I know there are results in this direction and many open questions. But
So what is next now? I mean, we have that for convex bodies is true. In complete generality is not true, but I mean, there is a huge.
It's a dead end. Yeah. Well, I mean, in a way, I think the interest in Fuglede's conjecture is now probably diminishing because I think most of the interesting cases have been covered. In full generality, there are counterexamples. For convex bodies, it's true. For connected bodies, it's not true because the counterexamples still work. And there is basically two more major things. One is dimension 1 and dimension 2. Dimension 2 is, again, I don't think it's very interesting in a way. Dimension 1 would be pretty interesting. And that is related to this Cohen-Meyerowitz stuff and understanding the tilings of the real line, tilings of finite groups. So I think that's the last really interesting part. But if you ask me, it's not really Fuglede anymore. It's more like understanding tilings and weak tilings of the real line, and in particular, it's periodic. So understanding tilings and weak tilings of finite cyclic groups. And you would think that surely there is a theory which characterizes. No, there is no such theory. So that's the Cohen-Meyerowitz conjecture, which aims to characterize tilings of cyclic. But you are right. This is, to my mind, that's the only major open question in this area.
Then maybe you have said, but what happens now in Z to the D? So if we are looking at the group is Z to the D, so what will be the Fuglede's conjecture in this setting?
Yeah, in this setting, the conjecture is always the same, where the tiling is the same as spectrality, and all the counterexamples work as long as the dimension is at least 3. So in that case, yeah, there are counterexamples in Z to the 3 and higher, but no counterexamples in Z and Z to the 2. And as I say, I'm not sure Z to the 2 how much that of an interest, but Z as a one-dimensional, I think it is interesting. And I don't place any bets, but it might be true.
Any more questions? So if not, let's thank Máté again.
And shall I tell you a solution of the challenge?